So we've seen linear approximation, and so we're still going to approximate the value of f of x. So approximating the value of f of x using Taylor and Maclaurin. Series. So these things that I'm showing you right now are not on the AP exam. So we're not going to worry too much about them for the AP, but they are interesting to note about how we use things to approximate a function value. So we've seen that a linear approximation was when we had a graph that maybe looked something like this, and you pick a value here. Well, you're trying to figure out what this point is, right? So this is x comma f of x, and you don't really know what that is, but you do have a pretty good idea about what this point is. So this is your nice x and your nice y. And what we did was we drew a tangent line right there. And so instead of actually finding the y value that we want, which is this one, we kind of just use the y value on the line instead, and hopefully it's close enough. But the question is, what if it's not close enough? What if you have something like this and you could get maybe a better approximation? So this is still my nice point at x naught comma y naught. And I'm still trying to figure out what this y value is right here. Well, what would happen if I used, instead of a line, instead of a tangent line, what if I used a tangent parabola through that point? Maybe the y value on the parabola was closer than this y value was originally. Who knows? Maybe I didn't use a tangent parabola. Maybe I used a tangent cubic function instead, right? And so maybe the y value on this cubic function is closer to the actual value. You can see it's getting pretty darn close, right? And so maybe it's not the greatest idea to use a tangent line, but maybe we can use a tangent parabola or a tangent, cubic function. And so on and so on. So really what we're looking for is a tangent polynomial. And that tangent polynomial, in a nutshell, I mean, there's way more to it, but in a nutshell, that's what we sometimes use what is called a Taylor series for. So a linear approximation formula is called a first order Taylor polynomial. So if we are trying to approximate around a value for x equals a, it would be a first order Taylor polynomial. What they say is centered at x equals to a. And really what it was the equation of a line. Y minus your nice value is equal to the slope of your tangent times x minus your x value. Or y equals y naught prime, x minus x naught, plus y naught. If you're writing it as a Taylor polynomial, they sometimes write the y naught value first. So our y value is here, and then y naught prime, x minus x naught. Or even if it's fancier, f of x is approximately, because these are approximations, f of x naught plus f prime of x naught times x minus x naught. So remember that all of these are just the equation of a line. So what if I want a tangent parabola? Well, this is called a second order Taylor polynomial. And a second order Taylor polynomial looks like this, that f of x is approximately equal to your f of x naught, your f prime of x naught times x minus x naught, and then your f of x naught double prime over 2 times x minus x naught squared. So this term is added on because of a lot of sort of background area about how Taylor polynomials work. If you want, you can always go online and sort of see where the sort of derivation of these Taylor polynomials come about. So a second order Taylor polynomial brings on the x squared sitting in here. So you can see the x squared sitting right there. And what it does is it adds on that second term. Sometimes this is called a quadratic approximation. And for questions or graphs that are sort of like parabola type shape, these are a pretty good approximation for your y value. So maybe what we could do is take a look at an example. Let's see an example. So let's do find the approximate value of e to the power of x squared minus 1 at x equals 1.1 using a quadratic approximation. So what we want to do is we want to figure out this x naught value. This is like our nice x. Sometimes we call it a in here. So sometimes it's f of x minus a and x minus a inside the brackets. It's really depending on the textbook that you read. But what we want to do is we wanted to figure out what a value of the nice x is. So if my function is e to the power of x squared minus 1, would I rather plug in x equals 1.1, or would I rather plug in a nice x that's really close to 1.1? And that is what we're going to guess right here. I'm going to choose 1 because it's really close to 1.1 and it's easier to plug in. So what we want to do now is we want to follow our formula. So my x naught value is equal to 1. My y naught value, or f of x naught, is going to equal to e to the power of 1 squared minus 1, which is e to the 0, which is going to be also 1. What we also need in our formula is we need f prime, our nice f prime, and our nice f double prime. So let's see what that's going to be. So f prime of x is going to be e to the power of x squared minus 1 times 2x. And so if I wanted to now find f prime of x naught, it's going to be e to the 1 minus 1 times 2 times 1. So that's going to be 2. If I move up from there, and now I have to find f double prime, well, that's buddy rule, product rule. So my first derivative, my first derivative is e to the x squared minus 1. So the derivative of e to the x squared minus 1 is e to the x squared minus 1 times 2x, while the second buddy waits. And then e to the x squared minus 1 waits times 2. If you want to pretty it up, we get something that looks like this. 4x squared e to the power of x squared minus 1 plus 2 e to the power of x squared minus 1. For our formula, our Taylor polynomial, we need f double prime of x naught. So I need to plug in x equals to 1 into here. So I'm going to get 4 times 1 squared e to the 0 plus 2 e to the 0, and that turns out to be 6. Now we're going to plug it into our formula. So here's what I get. I get f of x, or f of 1.1, is approximately equal to f of x naught. So my nice y value, here it is, 1, plus f prime of x naught, that's 2, times x. You know what? I'm just going to do my function first. F of x is equal to 1 plus 2 times x minus my nice x. And then f double prime of x is going to be 6 over 2 factorial, or sorry, 2, just jumped the gun right there, times x minus 1 squared. So what my formula turns out to be is f of x is approximately 1 plus 2x minus 1, don't multiply it out, and 3x minus 1 squared. This is called a Taylor polynomial, and it is used to approximate our value for a function. So this is a second order Taylor polynomial centered at x equals to 1. That's that nice x value that we talked about. So now if I wanted to approximate f of 1.1, I would just plug that in. I would get 1 plus 2 times 1.1 minus 1. and 3 times 1.1 minus 1 squared. So this is 1 plus 1.1 minus 1 is 0.1, so times 2 is 0.2. And then 1.1 minus 1 squared is going to be 1/10 squared, so 1 over 100. So this will be 3 times 1 over 100. So just making sure that you're understanding that. That's 0.1 squared, so that's going to be 1/10 squared. That's going to be 1 over 100 times 3, so 3 over 100, or 0.03. So what this is 3 times. So what we've got is 1 plus 0.2 plus 0.03, and we get 1.23 as our approximate value. Now, if you wanted to check that out on the calculator, I'm sure it would be very, very close. I'm thinking maybe I have my calculator somewhere close here. We'll check it out. Oh, I do have a calculator. So if I was going to plug in e to the power of 1.1 squared minus 1, actually, not just my approximate value, but actually, I'm going to get this. E to the power of 1.1 squared minus 1, and I get 1.23367. And so you can see that's pretty decent approximation to 2 decimal places to see how that goes. So that's what a quadratic approximation would look like. Now let's continue on. Let's figure out what they all look like. So the Taylor polynomial sort of goes on from there. So you can always have like a higher order Taylor polynomial, and it keeps going and keeps going. So here was what our first order looked like. Let's just go back for a second. My f of x is going to be f of x naught, my nice y value, and then f prime of x naught times x minus x naught. That's my first order. Our second order had f of x was equal to f of x naught, f prime of x naught, so it's got that whole line approximation, and then it added on f double prime of x naught over 2 times x minus x naught squared. Here's what a third order looks like. So this is all Taylor polynomial. A third order Taylor polynomial looks like this. You've got f of x naught, you've got f prime of x naught times x minus x naught. You've got f double prime of x naught over 2 times x minus x naught squared. And then you've got f triple prime of x naught. You'd think it would be over 3, but it's actually over 6 times x minus x naught cubed. And it goes on from there. And what we want to do is we want to see what the pattern really is for this one. And again, there's another proof for this, but I think we can just see the pattern. This is over 1. And this is also over something. So we can actually rewrite this as something. So notice that all of these numbers have to do with our factorial situation. So n factorial. So n factorial, if you think about it, 1 factorial is 1, 2 factorial is 1 times 2, which is 2, 3 factorial is 1 times 2 times 3, which is 6. All of those are sort of happening in these denominators. So the 3 factorial is going with my third, my 2 factorial is going with my second, and so on and so on. So really what it looks like is this. F of x is equal to f of x naught over 0 factorial. And remember that 0 factorial is defined to be 1. This guy is f prime of x naught over 1 factorial times x minus x naught. If you want, you can even throw in an x minus x naught here to the power of 0 if you want to, because this is now to the power of 1. Then you've got f double prime of x naught over 2 factorial times x minus x naught squared. You've got f triple prime of x naught over 3 factorial, that's our 6, times x minus x naught cubed. You've got the fourth derivative of x naught over 4 factorial times x minus x naught to the fourth, and so on and so on and so on. And if you actually go on forever, you will get the exact value of your function. So for example, if I went like this, you probably love this one. The sigma, which means sum, as n goes from 0 to infinity of the nth derivative of x naught divided by n factorial times x minus x naught to the power of n. So this whole thing is in your sigma. Let's test it. I plug in 0 into this thing. It's the 0 derivative. So the first thing that I would be getting is plugging in 0. I get the 0 derivative of x naught. Well, if there's no derivative, then it's just this guy. Over 0 factorial times x minus x naught to the 0. That's my first term right there. And then when I plug in x equals to 1, sigma means sum, remember, and I can plug in my first derivative of x naught over 1 factorial times x minus x naught to the 1, and so on and so on and so on. And because this sigma goes on forever, this would be the exact value of this function. If it stops somewhere, like here, third order Taylor polynomial, then it's an approximation for your value. And in fact, all of your functions like e to the power of x, e to the power of x, cosine x, sine x, etc., are all approximated using a Taylor polynomial. There is no real way to calculate these values, and so what they do is they estimate them with these Taylor polynomials and see what they are going with. Note, and this is another way that we can become famous, if our x naught value is equal to 0, we get this. F of x is equal to sigma k or n. Yep, I'll just put a k over here actually. Of n. We'll use the n again. So n goes from 0 to infinity of the nth derivative of x naught over n factorial. And because the x naught value is 0, if this is equal to 0 right here, all I'm getting for this guy is x to the power of n. So if I have that, this right here is called a Maclaurin series. So that means that our nice x, or the x that we're centered at, is going to be at x equals to 0. So Taylor when x is not equal to 0, and Maclaurin when x is equal to 0. So that's a good way of, getting famous and all that kind of good stuff. So what I want to do is I want to show you an example of, we've already estimated one, so I want to show you an example of how you might figure out how to use these things in a different way. So let's do an example for this one. In part A, it says find a Maclaurin series for f of x is equal to e to the power of 3x. So let's just do a Maclaurin series for f of x is equal to e to the power of, do I want to do 3x? No, you know what? Let's do 2x. There's a nicer pattern there. Okay, let's do e to the 2x. So the Maclaurin series is like the polynomial. So what you want to do is you want to actually see what the polynomial is. And remember that our x naught is equal to 0, no matter what. So for me to see the series, I really want to see what the pattern looks like. So I'm going to go through and I'm going to say, okay, this is what the series is going to look like. It is your f of x naught plus your f prime of x naught divided by 1 factorial x minus x naught, and then your f double prime of x naught over 2 factorial x minus x naught squared, and so on and so on. And we're keeping our x naught equal to 0, so it's actually just f of x is equal to f of x naught, so f of 0, f prime of 0 times x, f double prime of 0 over 2 factorial times x squared, f triple prime of 0 over 3 factorial times x cubed, and so on and so on. So let's see what our pattern looks like. For me to be able to do this, I'm going to start with f of x is equal to e to the power of 2x. F prime of x will be 2e to the power of 2x. F double prime of x is going to be 2e to the 2x times 2, so 4e to the power of 2x. f triple prime of x will be 4e to the 2x times 2, so 8e to the 2x. I'm seeing a pattern. The fourth derivative of x is going to be 16e to the 2x, and so on and so on and so on. That means that if I wanted to find f of 0, I would get e to the 0, which is 1. And f prime of 0 would be 2e to the 0, which is 2. And f double prime of 0 would be 4e to the 0, which is 4. And f triple prime of 0 would be 8e to the 0, which is 8. And f to the fourth derivative of 0 is going to be 16, and so on and so on. So what we want to be able to do here is we want to be able to see what our pattern looks like. That means that e to the 2x is approximately, until we get to the end, it's going to be approximately equal to this formula that we have up here. So let's just write some stuff out and see what we get. We get f of 0, which is 1, plus f prime of 0, 2x, plus f double prime, which is 4 over 2 factorial, which is 2x squared. And yes, I know that's also 2. And then we would get the third derivative, so 8x cubed over 3 factorial, right? So I'll just put factorials under here, 1 factorial, there's 0 factorial, there's 3 factorial, and we'll figure out what this is in just a second. The next one is going to be 16x to the 4th divided by 4 factorial. And I'm hoping that maybe we could just figure it out. The next one's going to be 32x to the 5th over 5 factorial, and so on and so on. Notice that we should be able to actually figure out that e to the power of 2x is exactly equal to this. Let's see if you like this sigma. K goes from 0 to infinity of 2 to the n x to the n over n factorial. Well, let's try it. Let's see what happens. If I plugged in 0, I get 2 to the 0 times x to the 0 over 0 factorial, which is 1 times 1 over 1, which is 1. Sigma means sum. 2 to the 1, x to the 1, 1 factorial. So that's going to be your 2x, which is right here. The next one would be 2 squared, x squared, 2 factorial. So that would be 4x squared over 2, which is again what we have here. So one of the things that as you're going into a second semester calculus, you're going to have to be very familiar with this kind of idea about writing stuff in terms of sigma. But for right now, we don't really need to. Right now, I'm just going to put dot, dot, dot so that you can see what that's going to look like. So that is my my Maclaurin series for f of x is equal to e to the 2x. Now, here's part B of the question. Without using L'Hopital, find this. The limit as x approaches 0 of 3e to the 2x minus 6x minus 3, all divided by x to the 4th plus x squared. And you're thinking, well, how the heck am I going to do this without L'Hopital? Of course, the first thing I'm going to do is test. So I get 3e to the 0 minus 3 over 0 plus 0. Oh yeah, and sure enough, it's going to be 0 over 0, right? But one of the things that you can do is you can realize that this e to the 2x, the way that we actually calculate e to the 2x was using this formula right here. This is the formula for e to the 2x. It's our polynomial equivalent for e to the 2x. So I could actually just plug that in. I'm going to move way over here to the left so that you can see what I'm doing. So I'm going to go 3 times e to the 2x. I'm going to squeeze so you can see it. This is e to the 2x. So I'm going to write the 1 plus the 2x plus 4 over 2 factorial is going to be 2x squared plus 8 over 3 factorial. So that's 8 over 6. So 4/3. I'll go 4/3 x cubed. 16 over 4 factorial, that's 16 over 24. Let's see, what is that? That's 2/3 x to the 4th plus, and I'll just put dot, 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 dot. That's 3 times that, which I've got, minus 6x minus 3, And in the denominator, I've got x to the fourth plus x squared. Okay, let's see what that gives us. I didn't actually need to move over that much, but here we go. Make it bigger for you again. The limit as x approaches 0. Look at the top. I've got 3 plus 6x plus 6x squared plus 4x cubed plus 2x to the fourth plus dot, 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 and then minus 6x and then minus 3. In the denominator, x to the fourth plus x squared. So the reason why I can do this dot, 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 dot is because eventually it's not going to matter. Because notice that just like when we did the definition of derivative, this 3 is going to cancel off. This 6x is going to cancel off. And what I've got left is a whole bunch of stuff on the top. And if you notice, I can factor out an x squared out of all of them. So if I now factor out an x squared, I'm going to be left with a 6 plus a 4x plus a 2x squared plus dot, 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 all the way along. And in the denominator, I can also factor out an x squared, and I'm left with x squared plus 1. The x squareds cancel. And our job now is to plug the 0 in again. And when I plug the 0 in again, I'm going to get 6. And again, the reason why I can dot, 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 dot this is because all these terms, just like we did when we did the power rule proof, they all turn out to be 0. In the denominator, that's 0, and I get 6 over 1, which is going to be 6. And this is one of the things that we use a Taylor or a Maclaurin series for, is to be able to also find limits without using L'Hopital. If I wanted to check it, of course, now that you know L'Hopital, you could figure this out. The limit as x approaches 0 of, what was the question again? Oh yeah, 3e to the power of 2x minus 6x minus 3 divided by x to the fourth plus x squared. It was 0 over 0, so I can L'Hopital it, and I'm going to get 6e to the 2x minus 6 divided by 4x cubed plus 2x. If I test this, I'm going to get 6 minus 6 on the top, which is 0 and 0. So I'm going to L'Hopital again, and I get the limit as x approaches 0 of 12e to the 2x divided by 12x squared plus 2. When I put the 0 in here, I'm going to get the 12 on the top and 0 plus 2 on the bottom, and 12 over 2, of course, is going to be the same 6 as we had before. But I'm showing you these Taylor polynomials because a lot of the times, if you're not going to write the AP exam and you're just going to go like maybe to UBC or something like that and take Math 100, Taylor polynomials are a big part of what they teach about how these polynomials work. And they do actually sometimes ask you to be able to do limits not using L'Hopital and specifically using these Taylor polynomials. As I said, I am scratching the surface of the Taylor polynomials. It's not really part of the AP curriculum for the AB section. However, like I said, at UBC, they do a lot of it in first semester. So if you want, you can always look up some stuff online about things that are like Taylor error. We didn't touch about that. And even more examples about Taylor polynomials. Try some of the homework questions too. They are kind of little interesting questions, so I think that's it. That's all I need to talk about for a Taylor polynomial. Enjoy it, and see you later.